So we have previously seen how data is organized on disk, and we have also discussed that access to main memory is much faster than access to disk. So the idea behind database buffer management is to allocate some space in main memory. This is called the database buffer. And inside the buffer, there's space to put pages that are loaded from disk. So the hope is that pages which are loaded into the buffer are used more than once, because then every time we want to access a block, and the block is already in the buffer, we don't have to go to disk and waste 10 milliseconds access time for a disk seek, for instance. So this has of course consequences, because now we always try to go to the buffer first to fetch a page or a block. And if this page is not in memory, we have to go and load it from disk. So we always go to the buffer first, and hopefully we find the page there. If not, we have to go to disk. If we want to now write like a change to this page, we also do this in the buffer. So it can happen that a change is done in the buffer, but not yet written back to the disk, because if we would write back immediately, then there's also the need to spend these 10 milliseconds to write the the block back to disk. And we don't want that in general. And then multiple not so nice situations can happen. For instance, we have here like a change made to the entry of page C. So we change the record C to C prime. So now as we can see, on disk there's still the old value, and in memory, in the buffer, there's the new value. So now it could happen that the database system crashes and the buffer will be lost because the memory is assumed to be not persistent. And now the change is not really written back, right? So now what can we now say about the change made? The user walking away from the database system maybe assumes that the change was done, but this was happening only in the buffer and not on disk. This will be a topic later on when we talk about transaction processing. The other situation can also happen that the change was written back to disk. For instance here, this A prime is the same as in the buffer. Now it could happen that the user says abort, so the transaction would need to be cancelled, and then we have to go back to disk here and somehow revert that A prime into the old A. Also this undo is also part of the chapter on transaction processing. What we are concerned now in the next minutes is to understand why database buffers work and what are different strategies in order to kick out pages which are seemingly not required anymore to make space for pages that are more recently or more frequently accessed. The overall question in database buffer management is, which pages should we put into the buffer? And there's a not very concrete algorithm, but like a quite famous rule in a paper proposed by Jim Cray and Franco Puzzolo. This is called the 5 minutes rule. And this is the following. Pages referenced every 5 minutes should be made memory resident. That means that pages which are frequently, in here 5 minutes, used, every 5 minutes used, they should not be loaded from disk, but kept in memory. Database buffer management has some differences to operating systems buffers. Databases have specific access patterns. For instance, if you want to read everything from a certain relation, select everything from relation R, for instance, then this is the sequential access pattern. So you're reading a lot of tuples from disk, one after the other of one relation. If you're using index structures like a B tree or B plus tree, then you have tree-like access patterns. And this opens also the benefit or the potential to do prefetching, because often in database systems we can predict which pages to load next. In order to understand these access patterns a bit more in detail, we introduce so-called page reference strings. That's a super simple concept because essentially it's only like a list of pages that we want to access. Here we use the term reference and not access, but you can take that one or the other. So a page reference string is a sequence of entries Ri, whereas every Ri consists of a transaction identifier and the page identifier we want to access or reference. This only tells us what we want to access, or which transaction wants to access which page. Essentially, it doesn't say anything about if this page is in buffer or on disk, just like the access pattern or the access sequence. And now in the next slides, we want to analyze these sequences, these strings, in order to calculate how local such a sequence is. So we can somehow predict what is the effect, or what would be the effect of a buffer. So in the following few slides, we assume that we have a database in place, and the database has executed a certain workload. That means a user or an application has written or sent different queries to the system. The system has executed the queries, and the pages or the blocks necessary to answer these queries, these are recorded, and now we can analyze them. So this is like only about analyzing certain workload in form of these reference strings. Here are two illustrations. I think it should be kind of clear what sequential search means. So you have multiple pages, PI, and you're reading them one after the other. If you have hierarchical access, I think it's also clear that it could look like this. So these page reference strings, they contain phases of sequentiality and locality. Sequentiality means that pages are accessed one after the other. So neighboring pages on disk are accessed one after the other. And locality means that a certain transaction is often concerned only with a certain set of pages and is not using too many different pages. So on this page, on this slide, we want to compute sequentiality. For that, we do the following definition. We define sequential reference sequence, SRS, as follows. If we have two successive references, Ri and Ri plus 1, so that means there's like a dependency that Ri is accessed, and then afterwards this Ri plus 1 is referenced, or the reference string contains this entry. And if these two pages which are referenced there are only one different or the same, the ID of the page, then these two references belong to the same sequential reference sequence. Yeah? So that means that these references are regarding the same or neighboring pages. And if we now look for a certain workload or for a certain reference string, we're looking at all of these sequential reference sequences, SRSs, then we can compute a measure of sequentiality. For this, we need to just know how long such a sequence is. So the length of a sequential reference sequence is defined simply by the number of different pages that are referenced within this SRS. So for example, we have the following page reference sequence, or string. And then we look at the sequences we see, so the sequential reference sequences. So we have A and B are neighboring. So now we're using the alphabet to make it a bit more convenient. We could also use numbers, of course. But here, these different characters, if they're one away, like A and B, then this is the same as defined here, right? With I plus 1 and I. So if you're looking at this string here, we have certainly this sequential reference sequence, then this one, and then only the small one here. And now we count how many different pages were referenced within these sequential reference sequences. So we see that here there's only A and B referenced, so the length is 2. Here we have D, E, F, so the length is 3. And here we have only H, so the length is 1. So now that means for this example reference string here, we have a sequence of length 2, 3, and 1 of 1. And this measure of sequentiality is going now and looks at the cumulative distribution of these sequential reference sequences. That means that if this is like the probability, of course, and this is the typical way you're writing like cumulative distribution, and the cumulative distribution looks like this normally, like just standard example. So this is 1, and then we can look at the sequentiality and tell how long these sequences are within our sample reference string. Yeah. So if you're looking at this, for instance, it tells that 1/3 of all sequential reference sequences have a length smaller or equal than 1, and 2/3 have a length smaller or equal than 2, and of course all are smaller or equal than 1. And this is of course only a simple toy example, but if you have many more of these page reference strings, then you can have much more like interesting distributions here, and then you can draw conclusions as to what extent your workload is showing sequentiality. And this allows you to understand how effective a buffer can be, or prefetching can be, if you have such a workload. In order to compute locality, we look at so-called working sets of a transaction. A working set W regarding time point t is a set of all pages that have been referenced within the last tau references. This parameter tau is called window size. And the cardinality of this W set is called working set size, small w. So basically this means we have a transaction, we look at a certain time point, and we look what is the distinct number of pages this transaction has accessed within the last tau references. This cardinality divided by the window size is called locality, L. And the average locality for this specific transaction is then the average over all the time points. So we sum up locality over all time points and divide by the number of time points we have considered. This is called average locality for one specific transaction. Here's an example how to compute working sets. So we have here the timeline and 3 specific points in time, T1, T2, and T3. We look always at the last 5 references, so the window size is 5. We have 2 different transactions, T1, T2. And if you go now to one time point T1, for transaction 1, we see here's transaction 1, here's time point T1. So we have A, C, and A, and again A. These are 5 references for this transaction T1. T2 we don't really care about now, we only look at T1. So we have 5 accesses, or within the 5 previous accesses for this transaction, there are 2 distinct pages that were referenced, A and C. So the working set is A and C. Yeah? So obviously the cardinality of this working set is 2. We can do, of course, the same and compute now for transaction 2 for time point t1 the working set. So note that this is now t2 we look at. So here's time point t1. Transaction 2 has accessed E, D, and B, so there were only 3 accesses. And these pages were distinct, so it's easy to compute. There were 3 distinct accesses here. And so on and so forth. Let's go to time point t3. I want to compute now for time point t3 for transaction 1, the window, like the working set. So there has been, this is one access, this is one access, this is one access, this one and this one. So these are 5 accesses. Now we look at the pages we have accessed, which is A, G, H, A. So the distinct pages are A, G, and H. So the working set size for transaction 1 at time point t3 is 3. Yeah. Again, so what is important here to note is that we only look at one transaction at a time. So this is one access for transaction 1, this is one, and we go back as the window size parameter tells us. So in this case it was 5. So we totally disregard that there were some accesses to T2 in the meantime, or between these references, access of T1. So we only look at T1. And for these 5 accesses, we look at the distinct ones, the distinct pages, and hence we compute the cardinality, so the size of the working set. And if we now do this and compute locality, for each of these counts we have to divide them by the window size. And if we want to get the average locality, we just sum up these individual localities and divide by the number of time points that we considered. In this case, it's T1, T2, and T3, so we would divide by 3. This is how you're computing locality, or average locality, to be more precise. As a last measure, we look at the so-called LIU stack depth distribution. It's another way to describe locality of access. Now this is very simple. Basically, we just take a stack, and whenever we access a certain, or we reference a certain page, we put this page on top of the stack. So basically that means it's a list sorted by date of the last reference. So now if we have a certain page reference string, let's say A, B, A, C, D, and then this works as follows. So initially, of course, we have only A in our stack, and then B comes in addition, so we have BA, and then A comes again, so we put A on top, and we have AB, and then C comes, and then we have ZAB, and eventually there's D, so we have D, C, A, and B is the content of our stack. And now what the stack distribution is counting is at which of the stack level, at the highest level or the lowest level of the stack, there was a page found in our page reference string. So if we're recording these positions where we found the page in the stack, this is giving you our give us our stack depth distribution. So if you look at the illustration here, on the x-axis we see the stack depth, so the position inside the stack. And this is the top position and this is the bottom position. And here we're recording the frequency of accesses to the individual position of the stack. And if you're looking at this green line, what is called here the high locality distribution, it means that if you're looking at a stack, here's the top position, here's the bottom position, that it's more likely to access a page which is positioned at the top portion or the top position of the stack. Yeah, so here's a high probability that you're accessing a very top stack position. So like a very previously used page. On the other hand, if you're going here on the right hand side, you see that for very low stack positions, so at the tail of the stack, at the bottom of the stack, it's unlikely that you would access a page which is positioned there. Why is this interesting? Well, if we have a pattern of access in our database that has a high locality in this sense, and we're choosing our stack to be of a certain size, let's say we have size k, then this distribution, the stack depth distribution, can tell us, if we go here to position k, can tell us, if we're summing up all of these values, it tells us what is the percentage of accesses that can be successfully answered by a stack buffer of size k. So LRU buffer of size k. Yeah? This is called LRU stack depth distribution. There's an example on the following page. I just want to refer also to the upcoming topic on database buffer management, or the strategies, where we will see again LRU as one of these replacement strategies, and then it will even make more sense to you. Yeah, this is how you're computing it. So you have again the illustration with stack depth on the x-axis and the frequency on the y-axis. And now how do you compute that for the reference string A, B, A, C, A, A, and so on? Basically, you have in the end, like initially, the buffer is empty, and then you're inserting A to the top position, and then B, and so on. And depending on the position that you access, you're going here to the histogram and you're counting one more for the individual position, the stack depth. So initially, assume that the stack content is A, B, C, D, E. And now what's happening now, you're accessing the first element here is A, and A, it's just staying at the top position. So you would add this one here. And then you're accessing B, and then B jumps to the top position. And now B was previously here, right, on the position 2, so we're counting one extra here for the position 2. And then we go again and accessing A. A is now at position 2, so we're counting one here for the position 2. We're incrementing that count. And then C comes, and we're currently here, right, and now C comes, and C was previously on position 3, so we're taking here this measure for C, for the stack depth 3, and then C obviously moves to the top position because it's stack. Then we're accessing A, so A moves to the top position, and A previously was on position 2, so again we have to here increment our counter for the stack depth 2. And then A comes again. A stays on the top position, but we have to now, for our histogram building here, or for our distribution building, we have to increment the counter for position 1. And again, same happens, A is again accessed. And then D comes, D is referenced, and then where is D? D was here on position 4, so we have to note this one down. And then D is accessed again. Yeah, so it stays at the top position, so we're incrementing this one here. And then eventually E is accessed, and E was here at the lowest position. And then this is our change here, the counter for position 5. So in the end, this reference string we have seen here, together with the initial content of the stack, gives us our stack depth distribution. Of course, only for this little toy data, but if you're doing this for very many reference strings, and you're looking at this distribution, like we have seen on the previous slide, and then this distribution can tell us how effective an LRU buffer would be of a certain size. Yeah? Because if the size would be 2, this means that we can answer all of these requests, but we could not answer these ones. And if this is a tiny fraction only, then we can say with a buffer of 2, we are quite good. So we can answer quite many requests, of course not all, but to a large extent this K buffer size would be effective. And this is the meaning of analyzing this LRU stack depth distribution.